acceleration in turn, r alpha, okay, and all these things. So we'll take a quick recap of these things to begin with today, and then we'll look at application questions and problems based on this. So let's begin. Okay, so let's begin by understanding the radial and tangential unit vectors once again first. So we can see that during a circular motion, if at any point of time the instantaneous position vector of the particle doing the circular motion is here, so its angular position is theta. Its angular velocity is d theta by dt. Its angular acceleration is d omega by dt, like this. Then first of all, we begin by explaining or by expressing the two important unit vectors: the radial unit vector, which is along the radial direction, and the tangential unit vector, which is along the tangential direction. So these two unit vectors are expressed with these special symbols r cap and theta cap, and they are related to the angular position by this cos theta I cap plus sin theta j cap. Similarly, the tangential unit vector minus sin theta I cap plus cos theta j cap. So once we have defined this, then using the general definitions of velocity, acceleration, etc. from kinematics, what we had seen is that in general the velocity vector will always be in the tangential direction in circular motion, whereas the acceleration vector in general will be in such a direction that it has two components. One component is tangential and the other component is radial or centripetal. The acceleration vector in general could be something like this. So velocity is r omega theta cap. So the magnitude of velocity is always r omega, where that is the property of the circular motion. And the acceleration vector we saw has the, in general, it has the two components, tangential plus centripetal, okay, where the tangential acceleration is given by the relation r alpha along the tangential unit vector, and the centripetal acceleration is given by the relation minus r omega square r cap. So the centripetal acceleration is pointing towards the center. It has a magnitude of r omega square, which can also be written as v square by r. Okay. Now, the role of the centripetal acceleration, it acts perpendicular to the velocity vector such that it makes the velocity vector turn. Now, all the time the velocity vector is turning as the particle is going from point to point. You can see the velocity vector is always turning. So that turning happens as a result of the centripetal acceleration that is responsible for causing the velocity vector to turn. Whereas the tangential acceleration, on the other hand, we've seen that it can also be expressed as rate of change of speed. So the role of the tangential acceleration is to change the magnitude of the velocity. It does not affect the direction, it only affects the magnitude. So it affects the magnitude of the velocity vector. Whereas the centripetal acceleration does not affect the magnitude, it affects the direction. It causes the velocity vector to keep rotating in direction or turning in direction. हेलो सर, हूँ ना सर, डाउट्स के लिए आया था 1:30, फिर BSM सर हैं, उस वहाँ पे बच्चा है नहीं, यहीं से बैठ के लास्ट टाइम के रेड हाउस का था, बच्चे नहीं आए थे फिजिकल लेक्चर के लिए। मतलब मैंने जनरली जो देखा डाउट्स के लिए आ जाते हैं, लेकिन फिजिकल लेक्चर के लिए कम ही आ रहे हैं। Okay, so let's look at a question with the application of this concept fully. So now we have this equation. We have a particle starting from rest but moving along a circular motion. Moving along a circular path whose radius is given to us, let's say it's 25 meters, okay, such that its speed is increasing uniformly with respect to time. Yeah, Aman, I'll scroll back. Just let's write down this question also first. Okay, so what we have to do here is first of all find its speed, its angular speed and angular acceleration as functions of time. Then also find out the centripetal acceleration magnitude and the tangential acceleration magnitude as functions of time. And then what we have to do is we have to calculate at t equal to 1 second, find the magnitude of acceleration and the angle between the acceleration vector and the velocity vector. So I'll just minimize this and scroll up so you can start working on this question if you finish writing down the earlier part. In any case, this is a quick recap of what we had learned in the last lecture, so it's already there in our notes. So basically start with the question now.
So can you please zoom in the question?
Yeah, so the question what is happening is that you have a particle that is moving along a circular path, okay, of given radius of 25 meters, but it's not moving uniformly like the previous question we have done in the last lecture. It's moving non-uniformly. How we know that? Because it's given to us that it's starting from rest and its speed is increasing. So that means it's not having a uniform speed. Its speed is increasing at a uniform rate of 5 meters per second square. So from this now we have to find out all these things. For example, we have to find its speed, its angular velocity and angular acceleration at any time t. Then we have to find the centripetal and tangential components of acceleration accordingly, okay, as functions of time, and then specifically at a particular instant of time t equal to 1 second, we have to find out these other factors. So basically everything you need to solve this question we have just discussed in the general equations above, which is the kinematics equations for circular motion. Okay, so anybody got the answer? At least the first part, it's pretty simple, right? How the speed is changing with time. The initial speed is 0. That's given to us because it's starting from rest. And then it's given to us that the rate at which the speed is increasing is uniform and it's 5 meters per second square. So that now means that initial speed is 0 and the rate of change of speed dv by dt is 5 meters per second square, which is uniform. So these two statements together, they can be used to understand that the speed at any time t is 5t. The speed is in meters per second. The time t is in seconds. So now we need to just use the definition that if v is 5t, then angular velocity or angular speed will become v by r. So that is 5t meters per second divided by the radius of the circular path, which is given as 25 meters. So angular velocity is 0.2 t or t by 5 radians per second at time t. And angular acceleration, which is d omega by dt. So that is 0.2 radians per second square. Okay, so this should be fairly obvious, right? So now let's come to the second part. The centripetal acceleration at any point of time has a magnitude of v square by r or omega square r, whichever. Okay. So you can see that the centripetal acceleration as a function of time here will just become t square. And the tangential acceleration on the other hand is r alpha, which is also by the way equal to dv by dt. So we already know that the tangential acceleration is 2 meters per second. So it's a constant magnitude, the tangential acceleration. So now we can understand this final part like this. If we visualize it, let's say,
Sir,
yes,
sir, how did tangential acceleration came 2 meters per second square?
because rate of change of speed was given to us, right? Or we calculated alpha. Okay, so you can calculate it as r alpha also. R is,
So R is 25.
then we have made some mistake. It should be 5, my mistake. Okay. It's 5 now.
Yes. Not.
The rate of change of speed dv by dt is also given to us as 5. Just make a correction. It should be 5. Right?
And centripetal acceleration as well should be 5t square.
So centripetal acceleration will become v square by r. Okay. So v is how much? It's 5t. So 25t square divided by r, which is 25 meters. That's how I got it as t square. Okay. For omega square r also you can write it as so. Okay, now to visualize the final part. So let's say this is where the particle is located at the time of 1 second. So it will have a velocity in this direction. This is your radial direction. This is your tangential direction. Now its acceleration is in some general direction like this, which we have to calculate the angle between these two. So if this angle is theta, you can see that this component is the centripetal component and this component is the tangential component. So if I just draw those two vectors separately over here, you understand that if this is the velocity vector and this one is the acceleration vector, at any instant for that matter, okay, and we want to calculate this angle theta, so we can also see that the components of the acceleration vector are such that there is one component which is perpendicular to the velocity, that is the centripetal component, and there is one component which is along the velocity or along the tangential direction, and that is a tangential acceleration. Hence, from vector algebra, you can see that. So first of all, at t equal to 1 second, the centripetal acceleration is, sorry, t equal to 2 seconds, it was, right? No, t equal to 1 second. Okay. So at t equal to 1 second, the centripetal acceleration is 1 meter per second square, and the tangential acceleration is uniform of 5 meters per second square. So the net acceleration's magnitude will become square root of centripetal square plus tangential square. So in this case, that will become the root 26 or very close to 5. Okay. But also this angle theta, that theta will be tan inverse of centripetal divided by tangential. So in this case, tan inverse of 0.2. Because centripetal is 1 and tangential is 5. Okay, so for t equal to 1 second, what we get is that the magnitude of the acceleration will be about, we do an approximate calculation. Nearly 5.1. And theta, if we calculate tan inverse of 0.2, So you can leave the answer in tan inverse, it doesn't really matter. I'm just giving you an idea of the value. It's about 11 degrees. That will be the angle between these. So you can always use this type of a question as something to revise the concepts of kinematics of circular motion, because all the interconnected aspects of it, like the relationship between angular parameters and velocity, angular parameters and acceleration, and all these things, they're included in this.
Sir, sir,
Okay, so now having understood this, all these relations here, now we'll move on to the next aspect of
Sir,
circular motion, which is about force acting on a particle when it is in circular motion.
Sir,
Yeah. Yeah,
sir,
but
I had a doubt.
yeah.
In the second subpart of the previous question,
Hmm.
so how did you wrote after AT is equals to R alpha and then sir dV by dt?
That is by definition, brother. That is a definition of tangential acceleration. And this had come in the previous lecture. How we had done it by that was by differentiating the velocity. So when we differentiate this velocity term, we get that derivation that the acceleration, which is differentiation of r omega into theta cap. So here in general, what is happening? R is constant, but omega and theta cap are variables. So you have this plus omega into d theta by dt. Okay, then you substitute theta cap as what we've written above. It is
Okay, sir.
minus sin theta cap plus cos theta j cap, and you apply that differentiation and all that. So from that you see you get the acceleration as these two terms, r alpha theta cap plus minus of r omega square r cap. So this is only called the tangential acceleration because it's along the tangential direction, and this is the centripetal acceleration. Now you notice about the tangential acceleration that writing it as r alpha, we can also write it as r d omega by dt, which we can also write as this, and therefore it is dv by dt. So it is rate of change of speed.
Okay, sir.
This statement that we written here, that is equal to rate of change of speed. So r into alpha is the same thing as dv by dt, which is why in a uniform circular motion, what happens? Alpha is 0 or dv by dt is 0. So there is no tangential acceleration. There is only centripetal acceleration.
Yes, sir.
This is clear now?
Yes, sir.
Okay. So this is something important actually as a problem solving method also, that if you are given the rate of change of speed, like in this problem, dv by dt, the rate of change of speed was given to us. So that actually directly tells us what the tangential acceleration is. The moment I've seen that I'm talking about the speed increasing at a uniform rate of this way, so this implies that the tangential acceleration is equal to 5 meters per second. So I can directly say that from this. Okay. This is how we related this here also.
Sir,
Yes.
sir, 11.3 degree, how did you get?
Oh, that I have used a scientific calculator, beta, or you can use a.
Achha, calculator, okay.
I've used that function. Or if you don't have a calculator, I mean, in the absence of calculator, one has to use the table, the log table, which has trigonometric values also. So that kind of booklet. So you're not expected to remember this value, huh?
Yes.
So you know how to operate the inverse trigonometric function in a scientific calculator, no?
Yes.
I wanted to calculate tan inverse 0.2, so I just will type in 0.2 and then apply the tan inverse function on it, so you will get the value of the angle in degrees. So you'll see it will come out to be close to 11.3 degrees. Okay, like that, if you check for tan inverse of 1, for example, you'll get 45 degrees, like that. Or tan inverse of 0, you will get 0. Or tan inverse of 1.732, if you try out, you will see it's very close to 60 degrees. It will be slightly less than 60 degrees, approximately equal to 60 degrees. Okay, so now we move on to the next part of circular motion, where we'll talk about forces acting on a particle, or the condition on net force on a particle when it is in circular motion. So this part is now called dynamics of circular motion. Okay. Dynamics is always to do with the laws of dynamics or Newton's laws, which is about force. So it's basically the same approach that we've taken to dynamics before. That is, we apply Newton's second law that net force is equal to mass into acceleration. Okay. That is the statement of Newton's second law. But now this is for the specific condition for. So in this, in a circular motion, okay, the acceleration vector will be the sum of tangential plus centripetal acceleration in general. Whereas acceleration will be just centripetal acceleration in uniform circular motion. because tangential acceleration is 0. So accordingly, what we do is that the net force, it is calculated by external forces have to be resolved in tangential and radial axis, rather than resolved in, we'll say they have to be resolved with respect to, or they have to be resolved along the tangential and radial axis. Okay, so if in general a particle is at some point of time over here in its circular motion path, and as it is going in circular motion, it has an acceleration like this. So whatever forces are acting on it, suppose F1, F2, some combination of forces is acting like this. So the forces have to be resolved along theta cap and r cap. Because the net acceleration is the sum of these two components, which are respectively along these unit vectors. Okay. You should also remember the special case of uniform circular motion. So in uniform circular motion, the net force just becomes mass into centripetal acceleration. So in fact, we call this the centripetal force itself. In other words, it is the force which provides or creates the centripetal acceleration. Whereas in a non-uniform circular motion, tangential acceleration will be non-zero. So therefore, the net force will have a tangential as well as centripetal component. Both the components will be there. So this is just to give you an idea of the general method that we will be using in the application questions. But once we actually get down to the numerical problems next, you will find it easier to understand these points. Okay, so let's now understand our first numerical example. Yeah, there's no specific name as such, but we can call it the tangential component of net force. One thing you have to understand better is that tangential force never.
Sir, can you please show the previous slide?
Yes, sir.
Yeah. Okay. So what will happen is that when we are in a situation of non-uniform circular motion, your net force will be neither tangential nor centripetal. It will have one component which is centripetal, it will have one component which is tangential. Okay, so that's why in non-uniform circular motion, I've written down this statement here that the net force will have both a tangential as well as a centripetal component. Okay. Whereas when we're talking about uniform circular motion, that is the situation where the acceleration is purely centripetal. So the net force also has to be centripetal. That means it has to be pointing towards the center. It should not have a tangential component. Okay, Adinath. Okay, so hope this is done now. Let's look at a very easy to understand and very fundamental example of a particle in uniform circular motion. So imagine this equation. This is the surface of, it's a smooth horizontal surface of a tabletop, let's say. You have like the surface of a carom board or something like that, which is in an ideal situation perfectly smooth, so there's no friction. Okay, so now this is not inclined. One has to understand here that this is actually the horizontal surface. It's a smooth horizontal surface. So the gravity vector is perpendicular to this, like this. Okay. Now what we do here is we take a thread of a certain length and we attach one end of the thread to something like a small peg on the table, so it can rotate freely about that. Okay, and the other end of the thread is attached to a particle. So this is a thread of length L is attached at one end to a fixed peg or nail or something like that, such that it can rotate freely around it. And at the other end to a particle P of mass M. Okay. So this is the experimental setup, let's say. Okay. Now what we do is that at t equal to 0, the particle is given an impulse or a push such that it has a horizontal velocity v0, okay, perpendicular to the extended thread. So make a free body diagram of this particle. Take the mass to be 2 kilograms and the length of the thread to be 1 meter. And calculate all the forces So we are now basically at t equal to 0. We are giving the particle a velocity along that horizontal surface of V naught, perpendicular to the length of the thread, with the thread stretched. So immediately, because the thread is of fixed length, it will get tight or develop a tension the moment we give this the velocity V naught. And the thread will not allow the particle's distance to increase with respect to the origin. It will force the particle to move in such a path by continuously pulling it with some tension force. It will force the particle to move in such a path that its length or its distance with respect to O for the particle that remains constant. That means the thread will apply the necessary force to keep the particle in circular path. If its distance from a fixed point O is constant as it moves, that means it's in a circular path. Now, can you tell me what type of circular motion this will be? Because it's attached to a thread of fixed length, we can see that it has to be a circular motion. But now if I ask you, within circular motion, there are different categories. So which type of circular motion is this? Can you tell me? Yes, very good, Adinath. Now, can you give me some reason why that is the case? How you can be sure that it's uniform circular motion? Okay, I'll give you a hint. Now, suppose the surface had been rough instead of being smooth, then would it have been a uniform circular motion? Yes, Amani, that's partly correct. So basically, see what's happening is that on the surface of the table, there is no friction and there's no other force which is acting tangential. So there's only the tension in the thread which is acting in the horizontal plane. The other forces are vertical, mg and normal reaction. Now, what type of force the tension is? It's a centripetal force. It does not have any tangential component. So because the tension of the string acting on the particle provides only centripetal force, it does not provide any tangential force. So the particle does not have tangential acceleration. Okay, so its speed remains constant, but the tension keeps changing the velocity because it keeps turning the direction of the motion. Okay? So the tension plays the role of the centripetal force, providing the centripetal acceleration, but there is no other horizontal force in the situation here. So there's nothing to provide tangential acceleration. So the speed remains constant. Hence, we can suggest that it's a uniform circular motion. So practically, of course, this will not be true because no surface can be perfectly smooth. But if we make it nearly smooth, we will see that for at least a sufficiently long amount of time, there will not be any appreciable change in the speed. There will be slight amount of change, but we can neglect that, even in a practical situation. Okay. So now, having understood that it's not only circular motion, but it's a uniform circular motion, now you can go ahead and try and solve the question. So you can make the free body diagram as the first part suggests, and from that you can calculate all the forces acting on the particle given these details. Yeah, so the question is, na, matlab, Adinath, the idea is centripetal force is not some additional force. Centripetal, the term centripetal only means that pointing towards the center. So some external force only has to provide that centripetal force. So in this case, which is the external force which is providing the centripetal component of force? It is nothing but the tension, because the other two forces which are acting, they are not in the horizontal plane. So they don't have any centripetal component. Understanding? No? So tension itself is the centripetal force in this case. Yes, exactly. That is the point. So the force which points towards the center and provides that necessary centripetal acceleration, that one is called the centripetal force. It's given the special name. So if you visualize, for example, the top view of the particle as it is going in the circular path, see that at any point of time, in its path, tension is always acting on it in such a way that the direction of the tension is along the thread, and the thread is lying in the radial direction. So when the particle is here, for example, tension is acting like this. By the time the particle reaches somewhere here, let's say, at speed v0. Okay. Once again, if you look at the side view instead of the top view, you'll be able to see the other forces which are also acting. So as the particle is going around in this circular path, at some point of time, when it's, let's say, here, velocity vector is perpendicular to r, and now the forces acting on it are mg and normal reaction, which are vertical forces, whereas tension is the force which is horizontal and acting towards the center. So mg is vertically down, normal reaction is vertically upwards, and the two balance each other. Whereas tension, this is in the horizontal plane. And always pointing to the center. So tension is the centripetal force in this case. Okay, so 2 kgs, length 1 meter of the thread, and speed v0 5 meters per second. So 2 into 5 squared divided by 1. So we have a tension of 50 newtons. Whereas you can see the weight is 20 newtons. Normal reaction balances the weight, so it's 20 newtons. So you can understand the importance of the tension in the thread to maintain this circular motion, because that's the force which is providing the centripetal acceleration. If you cut the thread at some instant while the particle is in this circular motion, immediately the tension stops acting, and instead of continuing in the circular path, the particle is not able to turn anymore. It just goes off in the straight line tangential path. So that is the importance of that. The string's role over here, it keeps providing the tension, which in turn keeps providing the necessary centripetal acceleration. Without that, the particle will not be bound to the circular motion. It will just go off tangentially. Yeah, if you cut the thread, the not only the speed will remain the same, now there is no tension, so the net force becomes zero, so its momentum remains constant, so the velocity remains constant. So unlike in a circular motion where the velocity is constantly changing, even though the speed is constant here, if you cut the thread, there's no tension acting, so it just goes off with a uniform momentum. So there's no friction on the ground, yeah, on the surface. So hope this is clear.
Sir, can I just scroll up for a minute?
Yeah. Okay, done?
Yes, sir.
Okay. Now let's look at the type of example we were seeing earlier also, but in context of dynamics now. So let's say the diagram is just showing a part of the circular track. So this is the top view of a car being on a circular track. Whose the radius is 50 meters, okay, and the car is of mass 2 tons, 1000 kilos. On the first part, if the car moves at a uniform speed of 36 kilometers per hour, then find the net frictional force acting on its tires. And in the second part, instead of this, if the car moves such that its speed is increasing at the rate of 1.5 meters per second square, then find its acceleration, and once again the net frictional force. On its tires at an instant when its speed is 10 meters per second. So the first case, again, we are solving the dynamics, or we'll have to solve the FPD for the car while it is in a uniform circular motion. So uniform circular motion means that the acceleration is only centripetal. So that means that the net force acting on the car should be the centripetal force, or it should be centripetal in direction. But second case, it is one where there is non-uniform circular motion, because it's given clearly that its speed is increasing at a certain given rate. Okay. So for that, now we have to find the net force because of friction acting on its tires. So you'll see that that is neither centripetal nor tangential. It's something in between, because the acceleration of the car at that instant will have both the components. It will have centripetal component as well as tangential component. Okay, so once again, what we can do is look at the FPD. So the first case, when it's going at a uniform speed, of 10 meters per second. Yes, very good, that's correct. Okay, so that point of time, if you see the top view of the car while it is going in the circular path, its acceleration at any point of time will be perpendicular to its velocity. So accordingly, the friction acting on its tires should be like this. It has to orient the tires in such a way that the net frictional force that has to become equal to mass into centripetal acceleration. Friction acts centripetal, or you can say acts as the centripetal force. And this is like the top view. We also look at side view of the car as it is going in the circular path like this. See that the friction acting on the tires is like this, perpendicular to its instantaneous velocity, whereas there is also mg and normal reaction. GS 10. Yes, very good, Adina, that's correct. So now you can also work out that equation you've written, that vector equation. You can work out the magnitude of that equation on either side. So that magnitude will give you the magnitude of frictional force.
Sir,
Yes.
sir, friction should oppose the velocity in a relative velocity. So should be opposite to velocity.
This is not that situation. Okay, this is not a kinetic friction. Understand one thing: the wheels of a vehicle, unless it's skidding, they are acting on a wheel which is rolling on the ground. So a rolling object is not skidding. Okay, so the direction of friction is not opposite to the velocity. It is according to how the tire is oriented. For example, you'll understand one more thing. Like imagine a person running on the ground, and while he's running, his speed is increasing. He's accelerating. So what is the direction of friction that acts on the sole of his foot? Does it act backwards or forward if he's accelerating? It acts forward, na? You're following my point?
Backward.
अगर वो accelerate कर रहा है तो उसको acceleration कहाँ से आ रहा है? It's coming from the friction that the ground is providing, na? So what he does is he's pushing his feet backwards, na, against the ground. So friction is acting in the forward direction.
Yes.
Again, that is what type of friction? It's static friction. It's not kinetic friction. It's kinetic only if his foot slips on the ground.
Yes, sir.
Okay. So like that, a rolling tire, no, or a rolling wheel, it is not skidding on the ground. So the direction of friction is not opposite to the velocity. The direction of friction is actually decided by the rotation of the wheel and also the orientation of the wheel. So when you turn the steering wheel of the car, the orientation of the wheel changes. Okay. So that generates the friction in that sort of direction to provide centripetal acceleration. You understanding now?
So friction will always be centripetal.
In uniform circular motion, yes. Now in the same example, the second case we'll say it's a non-uniform circular motion. So it will not be centripetal. It will be such that it has both components. So whatever the direction and magnitude of friction in this situation, normal reaction and weight are balancing each other. So friction is the net force, no? So friction has to be mass into acceleration. So friction will be according to whatever your acceleration vector is. In a uniform circular motion, your acceleration vector is only the centripetal acceleration. So accordingly, friction's direction is also centripetal. But in the non-uniform case, the second case that we'll see, your acceleration vector is going to have both tangential and centripetal component. So accordingly, friction will also have to have both tangential and centripetal component. So it will have to be in some general kind of direction in between the centripetal and the tangential direction. The point clear, Vita? So I hope you understood this situation. So in the second case, we have a non-uniform circular motion, such that the rate at which the speed is increasing or the tangential acceleration is 1.5 meters per second square. And the centripetal acceleration is v square by r. So the centripetal acceleration is equal to 2 meters per second square when v is equal to 10 meters per second. Because the radius was given to me as 15 meters. General now friction will be in some sort of direction like this, such that it has a centripetal component as well as a tangential component. So net force only will be friction. Okay, so hope you understood the difference between the two cases over here. The uniform circular motion case where the acceleration is purely centripetal. So the wheel has to be turned in such a way, and the spinning of the wheel on the ground is happening in such a way that the friction is acting only sideways in the centripetal direction, providing only centripetal acceleration. But while it is turning, if you're also accelerating in speed, that is the speed is increasing, then the wheel is rotating in such a way that the spinning is generating a forward component of acceleration, and the turn of the wheel or the angle at which the wheel is with respect to the straight line, the tangential line, that is generating this thing, a sideways friction on the wheel, which is the centripetal component. So the net friction is the sum of these two components, the tangential and the centripetal. So that's why the friction, the net vector is acting along the diagonal line which I've shown in the diagram. Okay, now let's look at another interesting example of circular motion and dynamics. So this time, imagine this kind of situation. We have let's say it's like a small little mound on which a person is running on. So let's say the center of curvature of this mound, the mound is perfectly spherical in shape. So the vertical line. The spherical mound or hillock, small hill kind of thing. It is of radius 20 meters. Okay. Now a person of mass 50 kgs is running up the mound at a constant speed of, let us say, 5 meters per second. That's a pretty high speed actually. But anyway, it's almost 18 kilometers per hour. Okay, let's assume he's running that fast. So when at the position shown, in which we'll take the value of theta equal to, let's say, 37 degrees, calculate the normal reaction force and the net frictional force on his shoes. So mass of the person is given to you 50 kgs. The radius of the spherical hillock, that is, or the spherical mound, is given to you as 20 meters. Take acceleration due to gravity as 10 meters per second square. 10 meters per second square. Okay, so when he's at this position where his angular position with respect to the vertical is 37 degrees, you have to make the free body diagram and from that understand how the forces of friction and normal reaction will be adjusting in such a way that he is able to move in this kind of situation. That is, he's running along the spherical surface up the mound at a constant speed of uniform or constant speed of 5 meters per second. Okay, let's work this out. So basically, when the person is somewhere here, now because he's moving at constant speed, his tangential acceleration is 0. But he's moving on a circular path, remember, so he's still has centripetal acceleration equal to v0 square by r, where r is that radius of the circular path. So if this angle is theta, now you can see on his body what are the forces which are acting. There is mg acting vertically downwards. There is normal reaction acting like this. And in order to keep moving at constant velocity, he'll have to push his feet back, hit his feet back on the ground with his strides. So that friction, static friction acting on his feet is like this, and he's able to maintain the constant speed. So you can see that tangential acceleration is 0. That means the net tangential force. So static friction should be able to balance mg sine theta. And centripetal acceleration is equal to how much? Here, 25 by 20, 1.25 meters per second squared. So now the net force pointing towards the center, that is how much? It is mg cos theta minus normal reaction, that is has to be equal to mass into centripetal acceleration. So that's our second equation. So from equation 1, we have so 300 Newton friction is required. Otherwise, that mg sine theta will start causing him to slip and lose speed. Okay. And from the second equation, you can see that normal reaction is mg cos theta minus mass into centripetal acceleration. So it's 50 kgs into 10 into 4 by 5 minus centripetal acceleration, which is 1.25. So it is 50 into 40 minus 1.25, so that is 38.75. So that is because Adinath, it's given to us in the question that the person is running at a uniform speed. He's running at a uniform speed of 5 meters per second, running up the mount. Okay. So to maintain that uniform speed, he will have to, his strides will have to be balanced in such a way that he's able to generate that much friction. So when he's at theta equal to 37, at that particular instant, he'll have to be able to generate a friction from the ground of this much by pushing his feet against the ground using his muscular power. So when you walk or run, you can kind of intuitively understand that with your rear foot, when you stride against the ground, you're basically pushing the ground in such a way that the ground is pushing you back with a combination of normal reaction and friction. So normal reaction is the thing that is balancing your weight, and the friction is the thing that is giving you, generating the forward acceleration. So in this case, instead of generating acceleration, it is balancing mg sine theta, so that there is no net acceleration.
So
Yes.
so that is 10 into 4 by 5 minus 1.25, right?
G cos theta minus centripetal acceleration, right? M I have taken common.
Yes.
Cos 37 is 4 by 5. Oh, I made a calculation mistake now.
That will be 8 minus 1.25, right?
8 minus 1.25, so that will give us how much now? 6.75,
Yes.
right?
Yes, sir.
Okay, so how much will this become now? Okay, this is correct now.
Yes, sir.
Okay, now let's conclude this part by understanding like a symmetrical problem to this one. But this time, instead of running up a mound, the person is running down a spherical, you can say ditch or something like that. The center of curvature. once again at theta equal to 37 degrees, you want to find the normal contact force on him and the net friction acting on his shoes. So I've given you the same values. Take the mass of the person also the same, 5 kg, 50 kgs. So this is a person running at uniform speed. Okay, so everybody got the answer in this? So the difference this time is, see, normal reaction is the force which is pointing towards the center. Earlier it was pointing away from the center. Normal contact force will act in the centripetal direction, so to speak. Okay? But you can't say it is the centripetal force as such, because even mg has a component along the radial direction. So it is actually, you will see, n minus mg's radial component, which will be the cos component. That is what is your centripetal force. Whereas friction, this time he'll have to apply sort of braking action using friction. Because mg sine theta will tend to give him an acceleration. So he'll have to punch his feet against the ground in such a way that friction is generated backwards as he's running forwards. So it's a sort of act of creating braking by friction rather than acceleration by friction. So once again, you can see that he has a centripetal acceleration, but his tangential acceleration is 0 because the speed is uniform. So tangential acceleration is 0 implies that here mg sine theta has to be balanced by static friction. So that's our first equation. So it will again show us that the static friction is 100 newtons at theta equal to 37 degrees. But now more importantly, n minus mg cos theta. The centripetal acceleration is this time normal reaction is mg cos theta plus mass into centripetal acceleration. It is 50 into 8 plus 1.25.
Sir,
Yes,
how did plus came? Can you explain?
because n minus mg cos theta is mass into centripetal acceleration. Now see the second equation that we've written, this one. What is the net force towards the center? It is n minus mg's component. Now, you understood?
Yes.
So if you break these forces into components, you can see normal reaction is acting towards the center directly, but mg's components are what? Mg's one component is mg cos theta like this.
Yes,
and
sir.
the other component is mg sin theta. So mg sin theta wale component ko friction has to cancel so that there is no tangential acceleration. But n and this mg cos theta in such a way that it's having an acceleration in this direction. So n has to be greater than mg cos theta by a factor of mass into centripetal acceleration.
Okay, so understand.
So that's the difference between this kind of curvature, whereas the other thing. So this is like he's running down a concave surface, no? And the earlier one you saw, he was running up a convex surface.
Yes, sir.
That's how that centripetal acceleration term affects n. There it was mg cos theta minus something. Here it is becoming mg cos theta plus something because of that difference. Okay, so this is clear, I hope.
Sir, why is friction backwards in this one?
So imagine you are running downhill, no? And you're trying to maintain constant speed. So how you will, push your feet against the ground as you're running? It will be a completely different orientation compared to when you're running uphill, no? Because you have to sort of create a braking action with your feet against the ground and friction generated, so that you don't slide forward because of mg's component.
Yes.
Understood? No?
Yes, sir. Thank you.
Okay, so people, with that we conclude today's session. And now, so you have the test coming up on Sunday, so do revision of relative motion very carefully, and also projectile motion and kinematics in general. Of course, also Newton's laws of motion and friction and all that. Okay, but circular motion is not part of the test, so do the revision for the test for the next 2-3 days. And after the test is over on Sunday, then you can pick up circular motion again. You can start doing questions from H.C. Verma, go through the solved examples, and you can work out up to question number 22 from H.C. Verma's exercise in circular motion. We'll discuss some of those questions in class also next time. Also, you can start from the module, but first I would prefer you complete H.C. Verma, okay, at least up to question 25 or 28. So for this week's homework, you can do up to question 22. Okay, so that's it for today's session, people. Wish you all the best. Have a nice day and all the best for the upcoming test.
Thank you, sir.
Bye, sir.
Thank you, sir.
Bye, sir.
Thank you, sir. Bye, sir.
Thank you, sir. Bye, sir.
Thank you, sir.